Everyone. So today this video is going to be talking about Module 2 of the Chemistry Course 112 at Queen's University. And more specifically, we're going to look at geometric isomers and E and Z nomenclature. So today's presentation will mainly focus on what E and Z alkanes and cyclic compounds are, and then how to identify and name these compounds. Before we get into this, though, we will do a little bit of background information about stereochemistry, isomers, and chirality. So before we start getting into the presentation and talking about E and Z isomers, we need a little bit of background information, and that background information includes what is stereochemistry. So stereochemistry is the study of how molecules are affected by the way their atoms are arranged in space. It deals with the 3D conformation of molecules and has to do with what directions each of those connections is pointing to. Stereochemistry is very important to the study of chiral molecules. Now, as we get more into stereochemistry, we'll learn more about isomers. Isomers are defined as a molecule that has the same chemical formula but have different properties and structures. Isomers can be put into two categories: constitutional isomers or stereoisomers. Constitutional isomers are defined as having the same formula but different connectivities, whereas stereoisomers are molecules with the same formula and same connectivity but have different spatial arrangements of substituents. Enantiomers and diastereomers are commonly called stereoisomers, and we'll go more in depth into what these are later on. Next, we're going to look at chirality. Now, molecular chirality was discovered by Louis Pasteur in 1848 when he successfully separated the two isomers of sodium ammonium tartrate. Chirality is the property of a figure to make a non-superimposable mirror image of an object or molecule. And types of chiral compounds that you may see every day are drugs, sugars, amino acids, DNA, and enzymes. Now, as kind of a real-world application, you can look at your two hands, and you can see how they are identical. Yet no matter how you flip them, no matter how much you mirror them, they will never be the same. This is a definition of a chiral object, whereas in the picture, as you can see, a bottle left and right of a mirror is still the same bottle. So those are achiral objects. Next, we're going to briefly talk about what a stereocenter is. So a stereocenter is a point in the molecule where every connection is unique. Chiral carbon centers are carbon atoms that are attached to 4 different substituents that are placed on the corners of a tetrahedron. This is very important to keep in mind later on. Now, if you look in the image on the slide, you can see how there's a carbon in the middle. And attached to this carbon is a methyl group, a hydrogen, an ethyl group, and then a bromine. Meaning these are all 4 different connections, making this a stereocenter. Now, before we get talking into what stereoisomers and diastereomers are, we're going to talk about what they aren't. And what they aren't are conformers. Now, conformers are isomers that have the same bond connectivity sequence and can be interconverted by rotation around one or more single bonds. Conformational isomerism can involve the rotation around sigma bonds and does not involve differences in the connectivity of or geometry of bonding. Conformers can be totally eclipsed, gauche, eclipsed, or anti. And as you can see in the picture shown on the slide, the molecules are different by the way their molecules are arranged and rotated around a single bond. It's the same molecule, just a different rotation. Before we talk briefly about the 2 types of stereoisomers. Here we have enantiomers, and enantiomers are 2 stereoisomers that contain asymmetric carbon atoms and are related to each other as non-superimposable images. Next, we have diastereomers, and diastereomers are defined as compounds which have the same molecular formula and sequence of bonded elements but have non-superimposable mirror images. These stereoisomers are also defined as not enantiomers. So you might be taking this all in and wondering, how does this relate to me? How does this apply to the real world? Well, stereochemistry and chirality is very important, and you might be able to see some everyday examples, such as the difference between galactose, which is a part of the sugars in milk, and glucose. And we all know what glucose is. So the only difference between glucose and galactose is that galactose has one of the OH groups pointed out, well, the glucose has that same OH group, but it's pointing down. Yet, we see that milk doesn't taste sweet, and glucose obviously doesn't taste like milk. This is an example of stereochemistry in the real world. Thinking back to what the last slide said, we can know that diastereomers can have different chemical and physical properties from one another, despite having the same chemical formula. Now, there are a few characteristics of diastereomers, such as diastereomers other than geometrical isomers may or may not be optically active, and also diastereomers can have two or more stereocenters. They can have different physical properties, such as different melting points, boiling points, densities, and solubilities. And though diastereomers can show similar chemical properties, they will not show identical chemical properties. Diastereomers can also be separated from one another through techniques such as fractional crystallization, fractional distillation, or chromatography. Here we see two easy examples of diastereomers, and we can tell that the hydrogen and chlorine have been flipped between the two molecules. And in order to identify which molecule is an E or Z isomer, there's a series of steps to follow. The first thing we're going to do is we're going to identify and label the longest carbon chain, and then we're going to identify the functional groups. This is so that we can name the compound later on, and it's the same way we name organic compounds. Next, we're going to identify the highest priority group on C1 and the highest priority group on C2. We do this by picking the molecule or the element that has the highest atomic number. So between hydrogen and chlorine, it would be chlorine. And then we determine the relationship. So for this first molecule here, we see hydrogen and chlorine on carbon 1. So we're going to circle chlorine. And then we see bromine and fluorine on carbon 2. So this is an E isomer because they're on opposite sides. And in Z, the chlorine and bromine are on the same side. So this is going to be a Z isomer. So here's our first example. So the first thing we're going to do is we're going to label all the carbons. So we got carbon 1, 2, 3, 4, and 5. And over here we see our function group, which are double bond. And then so we're going to be focusing on this carbon and this carbon for our priority point. So for this carbon and carbon 2, we see that carbon is attached to another carbon and then a hydrogen. So we're going to circle and prioritize that carbon. Carbon 3, we see that we have another carbon and then a hydrogen. So we're going to circle the carbon and it's going to be on the same side, making it a Z isomer, more specifically Z-pent-2-ene isomer. Okay. So for our next molecule, we see that we have 4 carbon molecules on it. And here we see a chloride or chlorine and then another double bond functional group. So on carbon 1, we see that there's chlorine and a hydrogen. So we're going to focus on the chlorine. And then on carbon 2, we see it's attached to a methyl group and then alpha group. Because the methyl group is smaller, the ethyl group will be taking priority, meaning they're on different sides, so it will be an E isomer. More specifically, E1-chloro-2-methyl-but-1-E. Over here in this molecule, it's a bit longer. We got 1, 2, 3, 4, 5, 6, 7, 8 carbons on this chain. And then here we go again with our double bond, our functional group. And then we also see how on carbon 3 we have a methyl group attached. And then here we have a chloromethyl group attached. And then on carbon 7 we also have another methyl group attached.
but we're going to be focusing on the two stereocenters over here. So on carbon 1, we have a methyl and ethyl group attached. So obviously we're going to prioritize the ethyl group. And then on carbon 3, we have the methyl chlor group and then this other carbon group. And obviously because chlorine is a higher atomic number, we're going to prioritize that chlorine, making this another E isomer. More specifically, E4 chloromethyl 3,7-dimethyl-oct-3-ene. And now for our last molecule. So our last molecule, we're going to have 1, 2, 3, 4, 5. We're going to have an OH group over here attached to carbon 2. We're going to have a bromine group and a methyl group attached. And then we're going to have a bromine group attached to the last carbon. And then over here we see our double bond, our functional group. So we're going to focus on that. So on carbon 2, we have a carbon group and a OH group attached. Obviously, the OH group is going to take priority. And then for carbon 3, we have a bromethyl group attached, and then this long chain. But actually, we're going to put priority to this one as it attaches faster to the bromine. So since they're on the same side, it's going to be a Z isomer, and more specifically Z5-bromo 3-bromomethyl 2-methyl-pent-2-enol. So thank you all for listening to this presentation. I hope you learned a lot and enjoyed it. Thank you.